Good morning. So we are going to take a subject of power system analysis. So where in power system analysis we are having a code of 191 EE 622 power system analysis. So this subject only I am going to take today. So before going to subject power system analysis, so why for power system analysis? So analysis is nothing but where we have studied start from generation. So where our power system starts from generation, transmission, distribution, and then to the loop. So our power system starts from generation, transmission, distribution, and then to the loop. So starting from generation, so we have studied in the previous semesters about the generation of power. So where generation of the different thermal power stations with different thermal stations and then power stations you have seen. And next one is your transmission and distribution, where the generated power is transmitted and then distributed to the load condition. So these are the basics of your power system. And next one is you are going to start about the analysis. Analysis is nothing but evaluation of any quantity. Analysis is nothing but evaluation of any quantity. So here analysis is nothing but analysis of power system. So power system we are going to start our analysis. So before going to the evaluation, so we have started with what are the electrical quantities. You are going to electrical parameters we are going to see in our power system. So start with electrical quantities, real power, reactive power, apparent power, and fourth one is voltage and frequency. So these are the electrical quantities we are going to handle. This we can tell it as parameters. So these are the parameters we are going to handle in our power systems. So first, real power. So our notation is P. So P is nothing but real power. And then reactive power can be mentioned as Q. And apparent power can be mentioned as S. And then we all know voltage as V. And then frequency as F. So what does mean by real power? So each and every electrical component consume some power. So that consumption of power is nothing but called as real power. So real power is nothing but consuming electrical power is nothing but your real power. So real power unit is nothing but we can tell it as kilowatt or megawatt, anything. So generally we have megawatt conditions, and that is the unit of your real power. And then reactive power. So what is mean by reactive power? So consumption of electrical power, consumption of power or consuming of power is nothing but called as real power. So reactive power is nothing but where the reactive power moves to and fro condition in a transmission line. So where in a to and fro condition during the generation, and then it is transmitted to the transmission through transmission line. So the real power will be transmitted to the transmission line, through the transmission line. So this to and fro motion of your power is nothing but called as reactive power. So the reactive power will be mentioned as kVAR, right? And then or MVAR, megavolt ampere reactive. And next one is apparent power. So it is a root mean, that is RMS value of your voltage and current is nothing but called as apparent power. It is mentioned as kVA. And next one is your voltage and then frequency. You all know about voltage and frequency. So these are the electrical quantities of or electrical parameters we are going to handle in our power system. The best example of your reactive power, real power is nothing but if you take a coffee. So if you take a coffee, if you are going to pour your coffee from one tumbler to another tumbler, okay, so where your coffee is nothing but a real power, right? So you are going to pour your coffee from one tumbler to another tumbler. So where you are pouring your coffee from here to and to the down. So by doing this too many times, then you can get your froth. Froth is nothing but froth. You can get your froth. So froth is nothing but number what you are going to. If you take you are going to wash your clothes, you can get froth. So that is nothing but your reactive power. So to and fro motion of your real power. So where the froth is nothing but it is no way you are going to consume your froth. But it is something, it is loss from your reactive power. So that is nothing but that is the best example of your real power and then reactive power. So together of this real and reactive power is nothing but called as your apparent power. So if you take your power angle triangle, if you take your power triangle, and here is your apparent power, yes, and here is your real power, P, reactive power, Q, where S is equal to P plus JQ, so P square plus Q square, that is nothing but S. So this is your apparent power. So now we have seen what is your what are the electrical parameters we are going to handle in our power system, and the next one is your power triangle. So then we will move on to the first unit of your power system analysis, where your first unit is comprises of modeling. Modeling is nothing but we are going to they will give a single line diagram. So first we will start with, so what is meant by a single line diagram. So and then using the single line diagram, you are going to represent your single line diagram in terms of your reactance diagram or your impedance diagram. And then the first half of your first unit is nothing but per unit analysis, and the second half of your first unit is nothing but we are going to design your Z-bus model, develop an Z-bus model or a Y-bus model. Okay, ba? Z-bus model and then Y-bus model. So these are the content of your first unit. So start from your per unit analysis. So before going to per unit analysis, what is single line diagram? So where in transmission and distribution you might have studied about your structure of power system. So what you have studied? Structure of power system. So structure of power system, where it starts from generating station and then a step up transformer and then a step down transformer. So and then move on. Okay, ba? So this diagram is nothing but called as a single line diagram. So this diagram representation is called as single line diagram. So why it is we want to know about a single line diagram? Why it is represented as single line diagram? So we are telling it as generator. So generator na a full generator system cannot be drawn, right? So a representation of a generator can be represented as this. Okay, va? So this can be of generator. Okay, va? And then a transformer. Abdina, then transformer cannot be drawn. Okay, va? An ideal transformer cannot be drawn. So original transformer. So for that representation of your transformer, we are using this as an transformer representation. So representing your electrical components is nothing but called as single line diagram. So using the single line diagram, so where in power stations we have power engineers. So in the power engineers will represent your electrical component in such a way. So your electrical components start from your turbine, and then your motor, and then your generator, and then transformers. So these will be represented in such a way. So using this single line diagram, we are going to find your per unit analysis. So what is per unit? So why for per unit? Per unit analysis is nothing but where each and every electrical component. So we have started with generator and then transformer and then transmission line. So these are the components of your electrical or your power system. So in this component, each and every component has its own characteristics, and then it will be represented in such a way. So if you are going to take as a generator, so if you are going to take a generator will be represented as with reactance, a specification of your generator, reactance, so and then your MVA or KVA it will be represented, megavolt ampere, and then your KV value. KV is nothing but your kilovolt. So the voltage, megavolt ampere, and then reactance will be represented for the transformer. For a transmission line, so for a transmission line we have impedance. So it will be represented as impedance, and then kilovolt, and then megavolt ampere. So for each and every component has its own specification, and then the reactance, and then megavolt ampere, and then kilovolt will be represented, voltage, and then power, and then reactance will be represented for each and if you are going to analysis. So analysis is nothing but where we have a common point, and using a common parameter we analyze the situation. So for example, if you are conducting a test, so we are conducting a test, so mark is nothing but, mark is a parameter where mark 100 marks is nothing but a common parameter or a common unit for every student. So for not for a single student marks, and not for another student their performance, and for another student disciplinary activities. So no, we don't take any different parameters for each and every students. We'll take for a test, we'll take mark as a single parameter to analyze all the student as a common. So here we are using each and every component has different parameters. So we are taking a common parameter as per unit. So each and every component will be converted into per unit. So it is nothing but length will be measured in meters, and your weight will be measured in grams. So likewise your each and every power system networks will be represented as per unit. It is a unit, a common unit for each and every component. So a generator will be represented in terms of per unit, and your transmission line will be represented in terms of your per unit, and the transformer will be represented in the terms of per unit. Likewise. So for a single line diagram, for the given single line diagram, we are going to find the per unit value of your given component, and using this per unit, so using this per unit we can analyze. So per unit is nothing but a common point or a common value. So using this common value, it is very easy to analyze. The power engineers are very easy to analyze. So start from per unit. So how will you find your power unit? We are having a formula for per unit. So per unit is equal to actual value by ratio of actual value by base value. So this is the actual formula of per unit. So per unit is equal to actual value divided by base value. So if you are going to find a per unit of a generator for each and every component. So if you are going to find a per unit of a component, so this formula has been modified into Z per unit new is equal to Z per unit old value into MVA new divided by MVA old into kV old divided by kV new the whole square. So the same formula has been modified for each and every component. If you are going to find per unit value for a generator, motor and then for transformer, so this is the formula. So Z per unit old value into MVA new divided by MVA old into kV old divided by kV new the whole square. This is the formula. So here it is mentioned as old new. So what are the old values and what are the new values? So I have already started with the actual value and then base value. So for a common single line diagram, so they will give a problem in terms of single line diagram representation. So for a single line diagram, for a common problem, we will have base kV value, right? So we will have a base kV value and then base MVA value for throughout the same problem. Okay, well, for the problem, for each and every component have the same base value. So your kV value alone will be changed, kV base value alone will be changed after your transformer. Okay, well, so that we'll discuss while I am doing the problem. So why we have changed the kV value, but the MVA value, new base value, new base value of MVA will be the same for throughout the same problem. Okay, well, it will be the same throughout the problem. So MVA value will be the same throughout the problem, where your kV value alone will be changed after finding your transformer. Okay, so this is the basic formula, and this is your basic formula, and then this is your modified formula for each and every component. So now if you will start with the problem to find your per unit value. So where it starts from generator and then transformer and then the transmission line and another transformer and then your motor. So the specifications, so where the generator have 60 MVA, 20 kV and X as 9%.